In this video we're going to discuss one more important measure of distortion called the third order intercept point. We're going to see that this intercept point allows us to quickly calculate the power of distortion products, which is handy because the third order intercept point is often included on the datasheets of amplifiers. We're going to approach this new measure by plotting the first order and third order components of an amplifier's output on logarithmic axes. I've noted that the axes are logarithmic by indicating the units are dBm. The first order component of amplifier power shows up as a straight line with an offset. The offset represents the power gain of the amplifier, which will be A1 squared if both the input and the output of the amplifier are matched to the same characteristic impedance. The line is straight and has a slope of 1 because a linear term in a normal plot will still be a linear term in a log-log plot. Plotting y equals x is the same as plotting log y equals log x. Even though the definition of this line comes from a relation between output voltage and input voltage, we can still plot the line on power axes because you can write a definition of decibels in terms of input and output voltages. The third order component of the amplifier power shows up as a straight line as well, but it has a slope of 3 because the voltage curve that causes it is cubed. Extending our early analogy, plotting y equals x cubed becomes log y equals 3 log x on a logarithmic scale. These two lines intersect at some place on the plot because the third order line has a steeper slope than the first order line, and that point is called the third order intercept point, or IP3. Because the third order harmonic component is equal to the first order harmonic component at IP3, we can also say that IM3 is equal to 0 dBc at IP3. The input power that results in IP3 is called the input referred third order intercept point, or IIP3, and the output power that results from an input of IIP3 is called the output referred third order intercept point, or OIP3. OIP3 is related to IIP3 by the power gain of the system because the points are on the A1 VZP line. IP3 is impossible to measure directly because amplifiers would blow up if you applied IIP3 to their input. Creating a third order term the same size as the fundamental is way outside the practical capabilities of most amplifiers. So why keep track of IP3 if we can't measure it? We're most interested in IP3 because it's useful for calculating the power of intermodulation products. We do that calculation by defining some input power P in 0 and observing that P in 0 is some distance from IIP3. We're going to call that distance our backoff, or B. Because we know the slope of the first order and third order lines, we can find the power of both of those lines in terms of IP3. We know the first order line is going to be B below OIP3 because the slope is 1, and we know the third order line is going to be 3B below OIP3 because the slope is 3. That means we can write expressions for first order output power and the third order intermodulation power in terms of OIP3 in the backoff, which is the same thing as saying that we can use the vertical version of backoff to find the powers we care about. We can also observe that the distance between the first order output power and the third order intermodulation power is given by 2B. So we know how big the third order intermodulation is compared to the fundamental. It's worth noting that IP2 also exists, but it's often at a higher input power than IP3 because A2 is a small coefficient. When you're calculating your second order intermodulation products, you need to know that the second order term has a slope of 2 on this log scale graph, which means that your second intermodulation product will be 2B below OIP3 and B below the first order line. That's different from the third order product, which is 3B below OIP3 and 2B below the first order line. You'll occasionally find IIP2 or OIP2 on a datasheet, but don't bank on it. It's kind of rare. However, because some receivers care about effects near DC, specifically direct down conversion receivers, IIP2 can matter a great deal for those types of circuits. It's possible to calculate IIP2 and IIP3 for cascades of amplifiers using the formulas I've shown here, which are referred to as cascade formulas. Note that these are linear equations, they aren't in units of decibels. I don't use these often because I prefer to make a spreadsheet that tracks the power of each frequency component at every spot in the amplifier receive chain, even in between these two stages. However, these formulas convey one very useful physical insight, which is that the IIP2 or IIP3 of the first amplifier contributes more to the total IIP3 than the second amplifier. We can see that because the IIP2 and IIP3 contributions to the total equations from the second stage are discounted by the gain of the first stage. That's because the distortion products of the first stage are amplified by the rest of the amplifier chain, so even small distortion terms can be amplified to high levels. If you have more stages than 2, each subsequent stage is discounted by all the gain that came before it. So in summary, intercept points are hypothetical intercept points are hypothetical input powers where harmonics have the same power as the fundamental. You can calculate intermodulation power levels by backing off from intercept points, and IIP2 and IIP3 have cascade formulas.